speaker, who is Mark Fels from Utah University, and who will speak about variational, symplectic, and Hamiltonian operators. Mark, you're welcome.
Hey, well, thank you, Joseph, for inviting me to speak in the seminar. Let me just try to get this working, eh? Make sure everything works here. Yeah, so what to say? So this is a summary of a paper I wrote with Emrullah Yasar, who's in Turkey, eh? And it's based on when I first came to Logan in 1993. And so I'm going to try to explain how that, what I was doing in 1993 played a role in all of this and how I was thinking about some things. And so the very first part of the talk is going to be about what I call variational operators and the relationship with symplectic operators and how the variational pi complex plays a role in these things. Now, hey, can you guys hear me okay? Hello? Can you hear me?
Well, yes, we do.
Okay.
Just proceed.
Hear and see. Okay. And
Yeah,
so so that's sort of the first part of the talk. And then at the very end, a little bit of something on coverings and Hamiltonian evolution equations and a bit of a relationship with these variational / symplectic operators. Probably that last bit's known. It was just kind of an aside for me to figure out a couple of examples. So, but you know, we'll talk about that. I'll just talk a little bit about that second problem. It was just a little something at the very end of that paper to help me with some examples. But anyways, okay. So here's where it started for me. And this goes back to when I first got to Logan, and it goes to the multiplier problem. So starting with a system of differential equations or scalar, doesn't matter. Whether you can multiply that system by some function and get it to be identically equal to an Euler-Lagrange expression for some Lagrangian. And so here, this bold E is just the Euler-Lagrange expression or equations, whichever people like to term you like to use. And so that's a question, and this goes back quite a long ways. And so A here is often called the multiplier, and it goes back to at least Helmholtz, probably quite a bit longer than that. I'm not 100% sure, right? So anyway, I was looking at this problem with Ian, and when I came here, he was working on that as well. And I ended up going off and looking at the case of a very simple case of a fourth order ODE. Okay, and so if you have a fourth order ODE and you ask yourself whether you can multiply it by a function, and that function could depend on, say, x, u, ux, u double x, even up to u triple x, you're going to multiply that by a function and get it to be identical to a Euler-Lagrange expression. And so what happened was, after some grinding, I was able to find these two conditions that were necessary and sufficient. And so, the third derivative, so I hope everybody, this makes sense. This first condition right here, oh yeah, maybe you can see that. This first condition, just that it's, not more than quadratic in the third derivative. And then this other lengthy invariant must vanish. And so this was a necessary and sufficient condition. And this is, of course, contact invariant, the vanishing of these things. It's completely coordinate invariant. And so it's a pretty reasonably easy decision process, invariant decision process, to answer that question. And so
Mark, I'm sorry, you mean that the second condition must hold for some small f, yes?
Oh, sorry, that's the big F, my mistake.
It's
the same. Yeah, excuse me. Yeah, that's the same F. Oops. Yeah, I apologize. Yeah, so if you give me the big F and you plug it in, and if these things are 0, then there's a multiplier and a Lagrangian, and it's a really simple condition, local closed condition, easy to verify, eh? And if somebody just gives you a fourth order ODE, boom, off you go. And I think that's about the best you could possibly hope for in solving such a problem. And so these conditions came up out of the cohomology of the variational bicomplex. And another thing that comes out of the variational bicomplex is that if these conditions are satisfied, it's not that difficult to go off and find the multiplier and the Lagrangian. So the problem is very tractable, very solvable. It has a simple, necessary, and sufficient invariant condition that's checkable. Sorry about those. These little f's are the f right here. Off you go. You can check it. Okay. So that's pretty good. And so it's through the variational bicomplex this answer came up, and I felt I could solve that somewhat. Okay. Now, as I was looking at the arguments in the variational bicomplex that allowed the solution to that, something starts to show up. And it's a generalization of that question of whether there's a multiplier so start now with the differential equation. And instead of asking if there's a multiplier, ask if there's a differential operator. That when you apply it to your equation, you get an Euler-Lagrange equation or expression. Okay, so it's a little bit of a generalization. And of course here, if this operator is a function, it's just back to that first question about, is there a multiplier? But in general, this could be a differential operator. Okay, and this question starts to show up really naturally as one looks at how the multiplier problem is solved for equation. This shows up in the argument reasonably early on. So I was seeing this, and so what I wanted to do was try to study this question in terms of scalar evolution equations. And partly because at the time I was looking at this inverse problem for, say, ODEs, like that fourth order equation, but I was also looking at the papers of Dorfman, and there were some very similar things happening in her papers as what was happening in this inverse problem. And so that, and I was looking at the solution to the inverse problem, and I was like, they seem to be similar, but I couldn't quite figure it out. And so I left it for a really long time until Emrula came to visit, and he was interested in some similar questions. And so then off we went back to looking at how one could solve this particular question. Is there a differential operator? So you apply it to the equation, you get an Euler-Lagrange expression in the case of evolution equations. So that was, just strictly in terms of the variational bicomplex and this generalized notion of the inverse problem. And of course, you can ask this question outside of evolution equations. It certainly, you can ask it for any kind of differential equation. It's just generalizing the multiplier inverse problem. But since it looked similar to what was going on for these symplectic evolution equations, I wanted to see if I could make a relationship. And that's the point of the talk. Okay. And so here's a example, really simple example. It would just be the simple linear third order equation, ut equals u triple x. You differentiate that thing, and then of course it's the Euler-Lagrange expression for this Lagrangian here in the big E. Does everybody see that with my little hand? Little hand there. Okay. And then here's a little more complicated one, and it's the potential cylindrical KdV. This one was bugging me throughout this whole project. So the potential cylindrical KdV is given by, ut equals u triple x plus 1/2 ux squared minus u over 2t. That would be the cylindrical KdV, or excuse me, potential cylindrical KdV. And if you take the derivative of that equation and multiply by t, it's the Euler-Lagrange expression for this Lagrangian right here. Okay, is that all clear? Of course, one would have to calculate this. It's not,
yes.
I mean, I should probably have got Ian's program up and put a little demo and so on, but it would start taking quite a bit of time to do that, so I didn't do it. But it is kind of fun to just put that into the program, do the Euler-Lagrange, see what you get. Okay. So this is both of these cases. This has dx as a variational operator. This has tdx as a variational operator. Okay. And so here's as far as I was able to, where I kind of ran out of steam, is trying to figure out. Let me just go back to this. Trying to figure out for a third order evolution equation necessary and sufficient conditions for a first order variational operator, with the idea of maybe I can get a solution that's like the solution I had found for the fourth order ODE, just in the sense that this is probably the simplest possible case. Let's see if I can push it to the end using the variational bicomplex, okay? And so I'll tell you what the answer is. So I don't know if you can see that. I can't quite see the top. Can you see the top? I can't quite see that right here.
Yes.
Yeah, somehow there's something over it in my side here. So this is just the third order evolutionary case. And here's what happens. I'm going to just give the answer here, okay? So if I'm looking for a looking at a third order evolution equation, and I want to find a first order variational operator, so a differential operator of this form. So when I apply it to my ut minus k and I get an Euler-Lagrange expression, there's some necessary and sufficient conditions were somewhat similar to the ones I wrote for the fourth order ODE. And I was able to sort of combine them into the following situation. So you write down this function or this differential differential one form that has expression. Well, it's kind of long, but this thing kappa 2, k hat 2 right here, dx. Here it is. It's a bunch of derivatives of the differential equation. And this also some horrendous bunch of derivatives. And that this needs to be a trivial conservation law. Okay, so these were the necessary and sufficient conditions. And of course, just writing down the fact that the total derivative of this is 0, or the total divergence is 0, would give you a differential invariant condition very similar to the one I wrote down for the ODE, but of course, much longer. And so, and then sufficiency needs to be a total derivative. And so if it is a total derivative of a function, then you can actually determine exactly what this variational operator is. Okay, so this gives at least a necessary and sufficient condition in terms of local invariance. Well, I guess not quite that, but pretty close. There's essentially a local necessary and sufficient condition for the existence of one of these variational operators. Okay, and this came out of the same calculations, more or less, that one does for the variational bicomplex to figure out if there's a Lagrangian. Okay, just kind of generalizing that.
Sorry, Mark.
Yeah.
I ask a question. Jennifer Apontov, sorry. So this variational operator, why is it sought in this particular form? R and the same function half dxr. Why does it need to be in this form?
Yeah. So yeah. Good question. And this is probably not going to surprise a lot of people out there. For these things to exist, they need to be skew adjoint.
Okay.
So this is skew adjoint.
Okay,
that's probably not going to surprise anybody who's familiar with a lot of stuff that goes on with the variational bicomplex or even variational sequences, eh? So this operator, and that's a good question of why these all have that form. And let's see as we get a little further on, but this would be skew adjoint.
So it's not a restriction, in other words, it has to be like this.
It has to be, yeah.
Okay, thank you.
Yep, exactly, yeah. So there's a complete solution to this, almost in terms of local invariance, necessary and sufficient, coordinate independent, contact invariant, et cetera, eh? And so, it's pretty easy to go off. You take a look at the potential cylindrical KdV, which I wrote down a first order differential operator that made the thing variational. And here's that form kappa, and this is definitely a conservation law, and it's a trivial conservation law. And remember, if it's the gradient of log of r, then you build your operator from the log of that function, and that was the one that showed up in the potential cylindrical KdV. Whew. Okay.
Sorry, what is GH? What is GH?
Oh, that's the gradient, the total gradient, I guess you would call it. There's different, so this kappa here is a conservation law, but it is a trivial conservation law. So there's I'm gonna define DH down the road, but it just says it's a trivial conservation law. So it's the gradient of log t.
So GH is just horizontal derang, yes?
Yeah, just the horizontal derivative. Yeah, exactly. But in this case, it doesn't mean very much because it's kind of trivial, right? But let's bump it up to maybe a little bigger one here. So here's the Kirchhoff-Novikov or the Schwarzian KdV. So if I take this equation, I crank out this form I call kappa, crank it out, and this is what you get. And then the question is, so this turns out to be a conservation law. It's very easy to check this is a conservation law, but it is I guess the horizontal. What do people usually like to use as the term for that? You know, this is a trivial conservation law. It's a total gradient, I guess.
We call it horizontal derang differential.
Okay, yeah.
But well,
Yeah.
You
But
can
it's
call
like a
it
gradient,
how
right?
you like.
Yeah, it's like a total gradient. You know, there's a number of terms for that, and I didn't want to kind of be too particular. This is a trivial conservation law. It's the gradient of the log of ux minus 2. And so that this term right here is the term you use to build the operator right here. Okay. So DH is, just depends. I know people, this is a trivial conservation law, and then this log ux minus 2 is the thing whose gradient, if you want to call it the gradient, or the horizontal derivative is this conservation law. So this is a trivial conservation law, and it's like its potential here gives rise to the operator. Okay, is that somewhat clear? Joseph?
Yes, it's clear, yes.
Okay. Yeah, so then, if I take the KdV and I just go calculate that form kappa, and this is not even a conservation law, and so there is no first order variational operator for this equation. Okay, so of first order. And, again, as it was asked, of that type that was written down, so it's not much of a restriction though, by the way. But anyway, so that has none. So it's pretty easy to detect whether these things in an invariant way, whether these things have these operators. Okay. All right. So what I'd like to do is give sort of a little bit of information on the bicomplex and how this solution comes up, and explain what's kind of the result in the paper. So I have to do a little bit of bicomplex terminology, and unfortunately, that's almost impossible in a short period of time. So if you know it, I'm barely talking about it, and if you don't, I'm going to try to say enough so some of the things make sense. Okay. So on the jet space of functions of two variables, one function of two variables, we have the total vector fields, which generate the Cartan distribution if you want. And I'll just call big DT as the total time derivative, dx is the total x derivative. And just so for nomenclature, I'm going to put a u sub I to be the ith x derivative, because that's going to play a role, and t sub I will be the ith x derivative of ut. These won't play such a big role, but we have on this jet space the contact forms, just the standard contact forms, which I write as script theta I ai for these different contact forms. Okay, and by dxi, I just mean repeatedly derivative. Okay, and I think if you know it, this is nothing. If you don't, it probably hardly makes any sense, but I'll try to explain what I can throughout here. Okay. And so the contact forms together with dt and dx give a coframe on this jet space. And so using this coframe, you split up the forms into things that have, say, R012 horizontal degree, or S greater than or equal 0 contact form degree, or vertical degree. And so, it's just a really simple example, because there's a lot of notation here, and if you know it, it's easy. If you don't, it's hard to keep track of it. And so and this is going to play an important special case anyways, is if I have look at a 3 form, which has this first denotes how many dx's and dt's, and the last one is how many contact forms. And of course, the coefficients are just functions on this jet space. And so here, this form, which is of 1 horizontal, 2 vertical, it has a dt term and 2 contact forms. This has a dx term, 2 contact forms. And so it's a 1-2 form in the bicomplex, so-called. And I'll keep repeating the meaning of these numbers for people that aren't familiar with it. If you're familiar with it, it's easy to remember. If you're not, it's like, what's that one again mean? So anyway, you know, on the bicomplex, there are 2 differential operators, and one is the so-called horizontal differential operator, dH, and it shifts the horizontal degree by 1. And so, you know, one way to calculate it is you have a form, and you just wedge dt with the lead derivative, the total lead derivative with respect to t, dx, lead derivative. This is just a formula for it. And there's also the vertical differential, which shifts you s vertical degree up to s plus 1. And its value on a function is really just differentiate with respect to u and its derivatives, and then multiply by the contact forms of that degree. And so this is sort of just a local formula for it on functions. And here are some of its properties, okay? And so probably the most important properties of these operators is dH squared is 0, dV squared is 0, and they anti-commute. Okay, so those are some properties. And it's reasonably easy to keep track of this by writing this diagram here. And there's some important, I might take this out of full screen mode because I wanted to write on it. If I could just for a second, eh? So I just want to write on this for 1 second. Can you still see it? Can you still see that?
You lost full screen again.
Yeah, but I wanted to write on something, and I'll switch it back in a second.
Okay.
Okay.
I understand.
So, right. So let me try this. Hey, what's going on here? Oh, yeah, I guess I got to do this. So here's this bicomplex, okay? So what is this thing I just circled? These will be forms that look, I thought I could write with the pen. Let me try. Hang on. I don't want to use this thing. Huh. Anyway, right here, these are Lagrangians, eh? Well, anyway, I'll just write it there. Those are the Lagrangians sitting there. You know, that's because of this 2. This 2 means these are differential forms which has a dt and a dx. They have no contact forms, so it's a dt dx times a function on the jet space, which you could view as a Lagrangian if you wanted to, eh? Okay. And you know, here's these shift you up 1 vertical degree, shift you 1 horizontal. We see our 1 there. So I'll go back to full screen mode. Okay. And so, yeah, these are shifting you. The dB shifts you, H shifts you, and so on. Okay. And this complex is exact in all of these arrows. It's kind of one of the important parts of this, that this complex is exact. So I'm just sort of stating some properties of this bicomplex, eh? And if you know this, it's yes, of course. If you don't, it's like, ooh, how could that be true? But it is, and it's a little painful to get through all the details of that. Okay, so we have that variational bicomplex, this differential forms, the differential operator sitting on the so-called free jet space. And so all I would like to do is now restrict all of that to the 0 set of a scalar evolution equation, just to keep it very specific, eh? And so I'm going to denote by here r infinity the coordinates on that infinite set or infinite manifold, just tx, u, ux, and then there's of course the inclusion from that manifold into the infinite jet space given by, you know, just the standard u is ux. Since the equation is given by ut equals k, you have ut equals k, and then to get the higher order t or x derivatives, you apply, this would be d by dt restricted to the subset R infinity. And so there are on that infinite R infinity manifold, that equation manifold, there are the time derivative or t total derivative and the x total derivative, which are just the restrictions of the ones on the free jet space. Okay. And so that's how you get that inclusion via those differential operators. Okay. And then on this submanifold of J infinity, we have the contact system as well, and I will denote those by theta 0 to theta I. And those will just be the standard contact system pulled back. Okay. Okay. So that's the setup that we have on this equation manifold. Probably getting a little hairy. And solutions, of course, to this scalar evolution equation are just integral manifolds of that, either the Pfaffian system generated by the contact forms or the distribution of t and x. Eh? Okay. And so the bicomplex all pulls back to this equation manifold. And again, what's going to turn out to be important here are differential of forms which have this a 1 here. So that's a 1 horizontal and 2 vertical. So what do they look like? They have a dx and some kind of a 2 form, which involves only the contact forms, a dt, 2 forms that involve contact forms. That would be a differential form on this infinite equation manifold. And here the coefficients depend, of course, only up to finite jets, but they depend on, just t, x, u, and its x derivatives and so on. Okay, so that's what a 1-2 form would look like. And we're going to focus a lot on 1-2 forms anyway. So there they are. Are they sort of clear to everybody? Raphael?
Yeah, it's clear, yes.
Okay, Raphael for sure. Okay, and the horizontal derivative restricts to a something like it's an anti-derivation, but it maps R, which is your horizontal degree, to R plus 1, and it's exactly the same formula. Wherever place the lead derivative with respect to total t derivative to the total t derivative on the equation, and similarly with the x. Okay, and that's just a way to calculate it. And then, of course, the vertical differential also restricts in this way. Actually, it's a little bit of a projection formula in there, but anyway. And they also have, again, the exact same properties as in the unconstrained case. And the only thing one thing that's quite different is that in the free bicomplex, the DH complex, the horizontal derivative, anything that's closed is exact, so that's exact. But here, there could be something in the kernel, the horizontal kernel, that's not in the image. Eh? So there's could be a failure of exactness, and I'm pretty sure everybody's very familiar with why this is important and what this has to do with, or something somewhat. And then, of course, the vertical differential is exact in this, stays exact in this case. So, right. And so the kernel here of this DH maps, which takes, let's just say something with a 1 and some sort of vertical degree to a 2 and same vertical degree, I'll just call these 1s conservation laws. And, here's a simple example. Of course, when s is 0, the kernel of this, of course, is just the conservation laws. So if I calculate, here's a differential form of type 1, 0. It's got no vertical. There's no theta forms in there. I calculate its total grade divergence, or its DH, and if you get 0, of course, you'd have to check that. And so that gives rise to a cohomology class, which is just how we often view conservation laws. This H10 is just the conservation laws modulo the trivial ones. And so that's just the standard terminology I think everybody's familiar with. But things get a little bit different when you change S from 0, which the kernel of this measures is the space of conservation laws for the equation. But once you bump that up to something non-zero, you start getting these, maybe we could call them vertical form valued conservation laws or form value conservation laws. So here's a form which I call eta. And you notice it is a one horizontal, but it has some vertical part right here. And then this is again, horizontal, one vertical. So it's a 1-1 form. So here's the contact form right there. And this thing, its horizontal derivative is 0, so its total divergence is 0. Yeah? Hello? Okay. And so it gives rise to a conservation law, a 1-1 conservation law. Okay? And curiously enough, by the way, and this is something that if you know a lot about this, this conservation law, this form eta, is not the vertical derivative of an ordinary conservation law. Okay, so if you have an ordinary conservation law, a 1-0 form, and you take its vertical derivative, you generate, because it moves it from 1-0 to 1-1, you do generate a form valued conservation law, but it's the derivative of a ordinary one. So in some sense, it's not as interesting as these kinds of conservation laws, eh? Okay, anyways, right. So it turns out that in terms of the inverse problem or finding variational multipliers or variational operators, the cohomology of H1, so the one horizontal, two vertical forms, which are closed, DH closed, turn out to be the object of interest in the multiplier problem and the operator problem. And so I'm just going to do a kind of a rough description of how that works. It's kind of detailed, and a lot of detailed knowledge of the bicomplex is involved in this. So, you know, if it's really hard to explain it in a small amount of time because of the terminology and the notation that's used. But anyway, I'll try. So in a paper of Ian and Nikki, where they were looking at the bicomplex for hyperbolic scalar second order PDEs, not such a big deal. You get a theorem, and this theorem works outside of that context, but you know, the arguments in there can be used in the case of what I'm looking at here, which is again a scalar evolution equation. And so what you can do is, if you have a 1s, so one horizontal, s vertical conservation law, there exists a normal form for these. Okay. And so if you so happen to have an equation and you somehow found one of these conservation laws, there's a little algorithm that maps this into a canonical form. Okay. And so, and this canonical form has the property that, well, it's again a 1s. It can be written as dx, 0th order contact form, s minus 1 order contact form, dt, s order contact form. And the rho satisfies the adjoint of the linearization of the equation. Okay, so that's a normal form argument for these 1s conservation laws. And it can be translated into finding it's equivalent to finding a solution to the adjoint here, right? Okay, and in the case S is 1, this of course is just this equation right here is just the equation for the characteristic of a conservation law, right? So it just boils down in that particular case to that, okay? And if you just look at this equation a little bit and try to figure out what the solutions are to it, the problem is that so these are differential contact forms, it's very hard for this to be true because of order type conditions. And so, you know, it's easy to show that for H1s, s greater than or equal to 3, there's no solutions, there's no non-zero row solutions. And so the cohomology vanishes at s greater than or equal to 3. No surprise, I think, to most people that are familiar with this bicomplex stuff. There's no cohomology there, but this also tells us why, another reason why 1, 2 becomes interesting. And so the consequence that there are no 3 vertical conservation laws implies that there are always DV closed representatives for every cohomology class of type 1 horizontal, 2 vertical. Okay. And also it's not hard to show that for even order, even for S equals 2, there's no cohomology there. Okay. So right. So I just want to explain why that cohomology class comes up in this problem. So hope everybody's sort of following me. So I want to explain why that cohomology is such an important spot. And so if you take a Lagrangian on the jet space, the free jet space, and you calculate its vertical differential, so just how does it vary with respect to u and its derivatives, you get the fundamental calculation in the calculus of variations is that this becomes the Euler-Lagrange expression plus the horizontal derivative of the boundary term. So that's the fundamental formula in the calculus of variations on jet space and in terms of the bicomplex. Everything good so far? Joseph? Hello?
I was muted by the host. Yes, it's clear. Thank you.
Oh, okay. Yeah, and so that's the boundary term, or is a boundary term. These aren't always obviously not unique, but there's a boundary term there. And so what happens is that if your Euler-Lagrange expression is equal to a differential operator applied to the equation, so if this is true, I can replace in the fundamental calculation in the calculus of variations, I can replace my Euler-Lagrange expression by my differential operator on the equation. And this is just an identity on free jet space. It has nothing to do with on jet, it's just an identity on free jets. And so on the other hand, if you take this identity and then restrict it to the equation, you pull this thing back to the equation manifold, of course, this term right here, ooh, look at that term vanishes, okay? Because it's equal, whoa, yeah, that term vanishes. And so this term pulls back and the boundary term pulls back. And so you have that the pullback of the Lagrangian is, or the dV of the Lagrangian is the dH of the boundary term. And so if you take the boundary term right here, and you calculate its its vertical derivative, this is where I should actually be writing things down, because it is a 1 horizontal, 1 vertical. You take its vertical derivative, it stays 1 horizontal, but it bumps up to a 2 vertical form. And this form is DH closed, and so this term lands inside that cohomology space 1, 2. And this is a mapping now from the variational operators into this cohomology space H1, 2. Okay, and this cohomology class is all, since it's dV of something, well, it's dV closed because dV squared is 0. And so anyway, this mapping that I just wrote down is the mapping that takes you from an operator into the cohomology H1, 2. Homology space, right? And so the proof that this is actually DH closed is just very simple. You apply DH to this form omega, which is dV of the boundary term. Use the fact they anti-commute and that d squared equals 0 in equation 2.4, right? So DH of the boundary term is dV. And so you're going to get dV squared of the Lagrangian, and so that's 0. And then there's the mapping, okay? So this gives a mapping from these differential operators, so-called variational operators for the equation, into the cohomology space H1, 2. Okay, and so this goes backwards. This turns out to be a bijection. And so how does this go backwards? And this is sort of when I was asked, like, hey, why are these operators look like this? It has to do with the fact of how this goes backwards, which is a standard argument in this inverse problem in the calculus of variations. Okay, and what you do is, if you have a cohomology class, you look for a dV closed representative. By vertical exactness, you can write that cohomology class as, or that representative as dv of a form, and here eta here is a 1-1 form. And then by the anti-commuting, if I take dh of it, dh of dv of eta, I get dv, excuse me. So I have this eta term, which is 1-1. I calculate its dh. This now becomes a 2-1 form. You calculate dv of that and you get 0. And again, by vertical exactness, this form dh is dv of lambda, and you get this little so-called snake diagram. So here you have, it's easier to just draw this in the diagram. Probably should have just done that. So yeah, whoa. You have this differential form omega that's dv closed, so it's a dv closed representative. You use vertical homotopy to find a 1-1 form. You map that over to a 2-1 form. This is dv closed, and so it's dv of some form. This form is on the equation manifold. And so what happens is you got to get into the trenches on this argument, which is this is kind of technical. And what it does, this argument, it's if you've got your omega and you've tracked this back, what it does is it produces for you the differential operator and the Lagrangian, which satisfy that condition that I wrote down, that the operator is the Euler-Lagrange expression. Okay. So that's sort of in a nutshell the relationship between H12, this cohomology space, and these so-called variational operators.
Mark,
yes.
This big file, it's onto, but it may have a kernel. Yes.
Right. So I'm gonna. That's the next statement.
Okay.
Yes. It is. And this. So this was a grind. Okay. This is in the trenches in that article. But so this turns out to be, so here's the mapping. Okay. So, and I've stated it in a funny way, but here's the story. If you have a variational operator, which I'll call E, okay, then, so if it's a variational operator, this is that H12 form. So here's writing all down the details of what that phi map is that takes the variational operator, builds the cohomology class. Here's the cohomology class. You take that operator, you apply it to the 0th order contact form, and that's this little piece right here. And then this is the full cohomology class. Okay. Now, so there's a converse to this. And so starting with the starting with the normal form for a cohomology class, which was right here. This was the form that was, say, in Ian and Nikki's paper. I massaged that canonical form a little bit to prove that every cohomology class admits a representative of this type, and therefore it's in the image of a variational operator. Okay? So this mapping is in fact a vector space isomorphism. And it was done via finding a canonical form for these cohomology classes and knowing how a variational operator maps to one of these cohomology classes. Who asked me that question? Somebody asked me about this mapping here, eh? This phi mapping, eh? Who asked me? Somebody asked me out there. And so here is that mapping. Here, this is the representative that's produced via that mapping. You know, in the previous statement, I just kind of wrote it abstractly, but here it is concretely producing this closed differential form. Okay. Any other questions? And so this mapping, this is exactly what you asked me. This mapping here is a vector space isomorphism from the operators to that cohomology class. And you know, the mapping from the operator to the cohomology is pretty soft in the way that that argument I gave on the bicomplex, how you can produce the eta and then take its dv. But to go backwards, required a pretty big grunge on finding a canonical form for these cohomology classes. That was kind of the grind.
So this homology group H1, 2.
Yes.
It may be understood as the group of symplectic structures. So you really state that.
Right. So that's the next thing I'm gonna do. Is that Joseph?
Yes, that's me. Yes.
Yeah, that's the next thing I'm gonna do.
So variational operators essentially are the same as variational symplectic structures. Yes?
Correct. That's what I'm proving next. Maybe I don't need to.
Okay.
Correct. But there is a slight difference. There is a slight difference, right? And so I'm glad you brought that up because I'm kind of curious your take on this. There's a little bit of a difference, right? And let's talk about that one when I put on the next thing. Hang on, I'm trying to turn up the volume here because I can't hear you very well. But you're right, and let's see how that matches up. Now, right, so yeah, so but anyways, here's the old Kirchhoff-Novikov Schwarzian KDV. Here is a variational operator. Here's the cohomology class. Kirchhoff-Novikov also admits this variational operator, and I didn't write down the cohomology class because it's big. Has a long expression. This is where Ian saves the day with his program, right? His program helped me out right here. I didn't write down the closed form, the cohomology class, eh? And here's another, and here's for the potential cylindrical KDV. Here's the operator. Here's the cohomology class, and potential cylindrical KDV. Here was a second variational operator for this. It's third order, and I didn't write down the cohomology class just because it's such a beast. Hey, it was just too long for me to include it here. But you know, there's the formula there in terms of derivatives you know, there's a formula, very easy to calculate that and write a little program to calculate the form. Okay. So here at the end of the day, the existence of these operators is equivalent to the non-vanishing of this cohomology class. The operators and Lagrangians, if you find non-trivial cohomology, you can use that little snake lemma it's called the snake lemma to find the operator and find the Lagrangian. Okay, so you take that, go to this canonical representative that determines your operator, use the snake lemma, find the Lagrangian, and then you're done. Okay, so now this is going to the question of, was it Joseph, did you ask me that question?
Yes, that was me. Yes, yes.
Right. Yeah. So let's dive into that question. Okay. And so for time-independent evolution equations defined in this way, you know, sometimes they're defined such that you know, what might make it symplectic. There has to be a symplectic differential operator, whatever that is. We'll discuss that in a second, and a Hamiltonian function, so that when you apply the differential operator to the K function, you get Euler-Lagrange expression of H. That's one way people sometimes define this. I'm not an expert in these integrable systems, but this is one definition. And so obviously the only thing I would say for me was it was pretty tough for me to track down a time-dependent formulation of this. So I had to kind of make it up. So here's what I made up. What would be the time-dependent? And it's essentially what you're saying, Joseph. So I'm going to give that here. So what you got to do is you extend the infinite jet space of R to R by throwing in a parameter T. Okay, and of course you have. So all this is I think, Joseph, of what you're saying is that this is mimicking how you might define symplectic forms on the bicomplex, but of course I've got to keep in mind that I might want T in there, okay? If I got rid of T, I would say this all agrees with everything that's somewhat standard in terms of Euler complex, eh? Okay, anyway, you got the total derivative, you got the contact forms. I'm just on J infinity RR, but I threw in a T coordinates, okay? And so what I want to do is I'm trying to define symplectic forms that I agree with how people write them in terms of Euler complex, but you've got to get rid of the T, the DT term. And so you can define the semi-basic forms, and these will just be differential forms on J infinity, but the coefficients, so ordinary bicomplex forms, but the coefficients are allowed to depend on T, but there is no DT in there. So those are the semi-basic forms, T semi-basic. And so, you know, a generic form here is going to be, here's a 1-2 form. It's got a dx, it's got contact forms, and it's got coefficients, which could depend on T, okay? And you still have the standard horizontal derivative. You got the vertical derivative. Now the horizontal derivative, again, because I'm excluding T in all of this, the horizontal derivative on this parameterized jet space just is ordinary dx. And they satisfy all the standard conditions. So I'm really glad you asked that question, Joseph. And on this space, in order to define symplectic forms, one has to use the integration by parts operator. That's part of, you know, this is all a lot of terminology here, but you have the integration by parts operators. And then inside the differential forms of type 1s, you define, I'll call these the S functional forms. They're just the image of the integration by parts operator, okay? And so, so what does that, this little integration by parts, what does it do is it takes a form. Let me go back here. Here, this thing right here. Oops. This is a 1-2 differential form. If I apply this integration by parts to that, what pops out is the 0th order contact form, and then another first order contact form, degree 1 contact form. And since it's degree 1, you can write it as a sum of these increasing degree or increasing order contact forms, eh? Higher DUs, eh? Okay, and so this integration by parts operator has a lot of tricky but useful properties. It's a projection operator. Its kernel is the horizontal derivative. And so you end up with something called the, I'm going to just skip down a little bit to the diagram. You get the variational, this is the variational bicomplex on J infinity RR right here. And then I've just, I'll think of it as including functions that are allowed to depend on T. And, you know, here is, this is the differential, which is dV integration by parts, dV integration by parts. And then you get this, the Euler complex, which I think, Joseph, you're probably super happy with that, right?
Yes.
Okay. And so so what's a symplectic form? A symplectic form then is just going to be a 1-2 form in one of those 1-2 functional forms. Okay. And whoops, gamma here, those are the evolutionary vector fields. I guess I should have put that in there. So you're looking for a 2 form, which is non-vanishing, and it's delta V differential. So it's, let me go back to this. So it's right here, but it's in the kernel of this. That's just this more or less a symplectic closed condition. Now this complex is exact, by the way. This is an exact complex, the Euler complex. And so a differential operator, I'll just define it to be symplectic if the corresponding one functional form is a symplectic form. Okay, so that's what I've taken to be as a definition of symplectic operator. Would you agree with that, Joseph? Hope so. Okay.
Oh, yes, thanks.
Okay, great. Yeah. And so the complex is exact. So, you know, there is a potential for it. So I'll just, and the potential, what is it? It's a 1-1 functional form. So it can only look like dx theta 0 times a function. And so there it is. There's the symplectic potential. And then, so then the question is, you know, anytime you have a symplectic form, you want to define what you mean by a Hamiltonian vector field. And in order to do so, I just took what they did in mechanics and if you have an evolutionary vector field, you define its suspension by just more or less including partial t in there. You extend it to partial t, and then you know, this symplectic, this differential equation, this scalar evolution equation will be a Hamiltonian evolution equation if its suspension differentiates the symplectic form to 0. That is to say, symplectic form is invariant under the flow of the suspension. Okay, and so this is all, you know, reasonably standard. But the only thing is that was bugging me in all of this is that here's the condition that I find if I have a evolutionary vector field, and now again the coefficients could depend on t, and here I have a Hamiltonian, and I want to know if it's a symplectic vector, Hamiltonian vector field. This is the condition that needs to be satisfied when there's a time dependency in there. I struggled to find that in the literature, by the way. Everybody assumes that, say, K and S, everything doesn't have a time dependency, but then you miss this term right here, which is part of the symplectic potential, eh? So I just couldn't find that in the literature. No sweat finding lots of stuff when there's no T in there. But all I did was sort of modify the time-dependent case of standard Hamiltonian mechanics, eh? And so, you know, if it's time independent, S is a, well, K is a Hamiltonian evolution if the operator on K gives the Euler-Lagrange expression. But again, when there's time dependency, you got to include the potential in this formula. Now, hey, I could be wrong. I kind of made this up and I never could find a good match for it in the literature. It's probably out there, but I didn't see it. But that turns out to be like, you cannot get rid of this term in what I'm about to say, okay? Okay, so it's what and Joseph was alluding to this. This is 100% correct. I'm not giving the details of this proof, but a form, so if you have one of these symplectic forms, then this evolution equation is Hamiltonian for the vector, is a Hamiltonian vector field, if and only if you take this operator, you build this cohomology class out of it. So this theorem gives a bijection, exactly what you're saying, between Hamiltonian vector fields for this type of symplectic form and this cohomology class of the bicomplex. So it's how to take the symplectic form and build this operator. So that was going back and forth. So these cohomology classes in the bicomplex will produce for you symplectic forms along with, so it produces the two things though, right? So that cohomology class in the bicomplex produces two things, the symplectic form and then Y as a Hamiltonian vector field for that symplectic form. It's producing those two conditions sort of simultaneously. And so this is kind of where I was struggling when I was reading the literature, especially when I look back to with Dorfman's papers, is that there seem to be quite a few papers that would say, hey, let's classify the symplectic operators and then figure out which systems are Hamiltonian with respect to those. This kind of combines those questions at the same time. So it doesn't try to classify symplectic operators or symplectic operators for Hamiltonian systems. It just finds the cohomology class that kind of answers the two things simultaneously. That's what the bicomplex does for you. Okay. Anyways, and it's Joseph, it's exactly what you're seeing. If you take one of these cohomology classes and you realize that first term, it's basically this term looks exactly like one of these symplectic forms. Okay, it has the exact same structure of one of these functional forms. Of course, this is on the equation manifold, so that can't be true. But you know, there's an obvious map that just says strip off that first term in the canonical form and try to build a symplectic form, and that's exactly what happens. But you know, you got to write out all the details of this too, because there's a little bit to write out. But that's basically it. Is that the density term is essentially a symplectic form on the free jet space cross T. Okay, so yeah, so exactly what you're saying. Okay, All right, so that was the relationship between these variational operators and the inverse problem in the calculus of variations and the theory of symplectic operators. Okay, so this very last thing was something I was looking at. What's my time on this? Do I have a time constraint? I can keep going.
Well, until 9 o'clock our time.
Oh, okay.
So
I mean, hey, you don't have to stick around but I do have a question in this part, so maybe you can help me. So one thing I was looking at trying to generate some examples of variational operators or symplectic operators and how this stuff is related to the Hamiltonian systems. Okay. And so if you have a first order Hamiltonian evolution equation written in this canonical form, right? When you go to potential form of this, so you just put z equal ux, plug that in there, and bring out that differential, and then integrate off the dx. There's the potential form, right? For that Hamiltonian evolution equation. Looks like that. Now, of course, how do you get from the potential form to the original form? It's just a quotient by translation in mu. So it's the quotient of 4.3. The quotient of the potential form gives you the standard form, and the potential form is a covering of fiber dimension 1, right? And so now if you apply the total derivative to the potential form, apply the total derivative, you just get back to this equation. But if you look at the change of variables in the calculus of variations, if you look at the variations of the Hamiltonian and do the substitution to potential form, how does that compare to the variation of the original and then do the substitution? That's the change of variables formula in the calculus of variations for differential substitution of this very simple type. Okay, and so this right-hand side of the derivative of the potential form, you can switch out this term for an Euler-Lagrange expression, and then it becomes so the derivative of the potential form is just the Euler-Lagrange expression for this term, and then the Hamiltonian with the substitution in it. Okay, so any of these first order Hamiltonian evolution equations automatically admit a first order variational operator. Okay, and so just with respect to that, I was trying to understand a little bit about trying to find invariant conditions that would guarantee a system is scalar evolution equation is Hamiltonian. Well, one simple condition is that there's a one-dimensional covering that has a variational operator, and characterizing equations with a variational operator is very easy in comparison. So I view that as kind of known or resolvable in terms of the invariance of the equation. The variational operator problem is resolvable in terms of the invariance of the equation via the cohomology space, eh? And so for the potential form, you have dx is a variational or symplectic operator for sure. And the Hamiltonian pulls back to Lagrangian. Everything works out pretty nice. And so, that's how I was thinking of how I could use this to build Hamiltonian evolution equations. All I got to do is write down a evolution equation with a variational first order operator, and then project everything, take the quotient, assuming it's invariant, take the quotient, build a Hamiltonian evolution equation, kind of inverting this process, right? Okay. So what happens in the case of a compatible system? A very similar thing happens. And so if you have here a Hamiltonian evolution equation with this potential form, and you have a Hamiltonian operator satisfying the compatibility condition, the potential form is going to have, this Hamiltonian be part of a Lagrangian in the variational operator problem. Okay, and the argument is exactly the same in that the operator, it's this compatibility condition allows you to trade off the little change of variables formula in the calculus of variations. And so this is not super, this calculation, I was going to go through it, but I think the examples are more interesting. And so what I was able to check was for third order compatible systems that the lift is symplectic, this lift operator is symplectic. And so it's a variational operator. And so you pick up a second variational operator or second cohomology class for the potential form. Okay. And so, as a converse to this, you can easily track it backwards. If you have invariant variational operators, they're going to quotient down to Hamiltonian ones via the converse of this. And so what I did is I looked at the cylindrical KdV here. Okay. And, this differential operator this is potential cylindrical. There's no U in it. It's invariant under translations in U. So it projects down and it's a variational operator. Here you go. No sweat. So it projects down to a Hamiltonian operator. And I ended up with, so this is the quotient equation. This is a form of the cylindrical KdV, maybe not standard variables, but it quotients down into a Hamiltonian system for two differential operators given right here. Okay. And here is the corresponding Hamiltonians for the cylindrical KdV. Eh? So here's the cylindrical KdV. These operators, you can find them quite easily for the potential form because they're variational operators, and they projected down to these. And so I was trying to decide if the cylindrical KdV was actually a Hamiltonian bi-Hamiltonian system, eh? And mainly, these Hamiltonian operators and the Hamiltonians were just projections of what was, variational operators and their Lagrangians from the potential form, eh? Anyways, I found this representation of cylindrical KdV via the quotients, and I really struggled to find this in the literature. I was hoping one of the experts on integrable systems could point me out, because what I was looking at was that some references say there are no Hamiltonians for the cylindrical KdV. And the only thing that was bugging me about all of this is that I'm not 100% sure I know what the time dependent definition is of Hamiltonians. I know it all makes sense for symplectic and variational operators. There's no problem there, but I wasn't quite sure what it would be for Hamiltonian systems, eh? So, but anyways, and another interesting one was if you look at the Schwarzian KdV, or the Kirchhoff-Novikov equation, this thing has two very obvious variational operators or symplectic forms, and the quotient, the quotient by translation in X, which is a symmetry of these operators, is the Harry-Dehm equation. And of course, the Harry-Dehm Kirchhoff-Novikov or Schwarzian KdV is just a one-dimensional extension of Harry-Dehm, and the symplectic operators for Kirchhoff-Novikov are just the lifts of the Hamiltonian operators for Harry-Dehm. So in some sense, they're essentially this, maybe you would think of them as the same equation. I'm not 100% sure. It's a one-dimensional covering, the Schwarzian KdV or Kirchhoff-Novikov of this equation. And the Hamiltonian operators are exactly lifting to the symplectic operators for Kirchhoff-Novikov and Schwarzian KdV. Eh? So anyway, I think that's about all I wanted to say. That's kind of what's in this paper. It was a long grind of formulas and stuff in the bicomplex, which is always kind of painful if you're not familiar with the combinatorics of that stuff, eh? So I think that's about all I wanted to say there, Joseph. So I think that's it. If you have any questions.
Yeah. Okay. Thanks a lot.
Yes. No, you're welcome. I'm glad I got to talk to you, because I know this is quite similar to some of the things. Let me see, quite similar-ish to some of the things you've worked on.
Mark.
Yes. Let me see if let me try to turn up the volume, because I can't hear you very well. Hang on. Let me see.
May I ask a question?
Yeah. Oh, yeah. Sure. Ask away.
Yes. Any ideas how to carry all this theory to the case of non-evolutionary equations, and also to multi-dimensional
right.
case?
I mean, great question. So, the theory of operator, variational operators, and I did try this, by the way, trying to pick out like the simplest possible case. Okay. So, what could you do with, in the simple cases, like this certainly makes sense in the case of ordinary differential equations, right? No problem. And that could go, going back to things like what Douglas had done, looking at variational multipliers or just the standard inverse problem for ordinary differential equations. And so I did try a little bit because, if you look at where things could be interesting, you could have for an ODE third order, of course, that will never be an Euler-Lagrange expression because it's odd order. So you could try to find a first order differential operator making the thing variational. You could do fifth order ODE, looking for operators making it variational. And so for odd order, you could look at odd order ODEs, odd order operators. You could do even order ODEs, even order operators. And those are all going to match up with the cohomology of the bicomplex. And, in probably the lowest possible settings and cases, you can, write down invariants that are necessary and sufficient for these operators. Now, one thing I ran out of steam to write down necessary and sufficient conditions for a third order. I was not tough enough, but that would give necessary and sufficient conditions in terms of differential invariance for the existence of a symplectic structure for an evolution equation. But I just didn't have I ran out of steam near the end to try to do that. So I don't believe that I've ever seen that written down, but it seems tractable. So, in terms of invariance, and so that would characterize evolution equations that emit a symplectic representation, right? But I don't know, I have not seen that written down, and it looked doable, but I was kind of running out of energy. I was only able to do the first order case when is a third order evolution equation, a Hamiltonian system for a first order symplectic form. That's it. So that condition I gave right at the beginning answers that question in an invariant sense. But to get complete answers in any other settings, and of course this operator idea works and doesn't really matter what the equation looks like, but to get closed form answers pretty tough in those cases, And so I haven't, Joseph, another one that I did, which actually I should have put it in as an example, but I completely ran out of steam as well, were some of the systems of symplectic evolution equations. Theory goes over there, no problemo. All those symplectic operators are variational operators for the systems, and they give rise to cohomology classes. And but I ran out of steam trying to take care of all of this for more variables, and even come up with some kind of a closed form answer on necessary and sufficient. Things got a little too hairy, eh? But the theory will go over for systems of evolution equations, no problem, eh? Yeah, so I did take the standard known symplectic representations of evolution equations and constructed the variational operators and cohomology class, but I just did a few examples instead of trying to come up with a general theory. This stuff almost killed me here, so anyways, so does that answer your question?
Yes, more or less. Thank you.
I mean, it's not a good answer, but I did write down for like fifth order ODEs. I took some fifth order ODEs and I said, okay, which ones of these admit first order variational operators? And you get an answer that's kind of similar, or characterization that's a bit similar to the thing I wrote down for the fourth order and a multiplier. It's kind of similar to that, eh?
Okay. Well,
not great, but
thanks. More questions, remarks, comments?
I have a question. Mark?
Yes.
Are there examples of third order evolutionary equations whose variational operators can be arbitrarily large order?
Right.
So
For
say,
the coefficients, you mean?
as differential operators.
Oh, the operators. Good
Yeah.
question. I struggled. I tried to prove, but again, here's where I ran out of steam. I tried to prove, that's a very good question. And what you're asking me is, can the dimension of that cohomology space be arbitrarily large for third order evolution equations? Because the operators give rise to these cohomology classes. And so if they're going of higher and higher order, you're going to start picking up more cohomology. And so could I prove, and I was not able to prove, for example, that for a third order evolution equation, the dimension of the cohomology is 2. Therefore, there's only 2, and they're of order like 1 and 3. I was not able to do that. So I
But there are
wasn't
no
able to.
counterexamples to this either. Am I right?
Pardon me?
There are no counterexamples to this statement either.
Nope, don't know. Nope.
Okay.
Great question. And I tried for a little bit, but the computations were kind of rough. And by the time I realized what was all going on and got all this written down, I was pretty sick of it. But I was hoping I could prove some theory on the dimension of these cohomology spaces, but I never could. And that would limit, for example, what the order of the operators are. But I never could.
Thank you.
Yeah.
Thank you. More questions?
So, but it's a really good question. But yeah, and I was hoping somebody here would have a good reference to the time-dependent formulation of Hamiltonian Hamiltonian evolution equations, either in the symplectic case or but I've never really seen one. And and whether if anybody has a good reference on the cylindrical KdV. There was one reference I was looking at that said it's not Hamiltonian. So I'm not sure, not by Hamiltonian, I guess. But it certainly admits 2 Hamiltonian operators that are compatible, but I don't know if I didn't go check all the conditions, and anyway.
Mark, hi, Boris here.
Oh, Boris, what's going on?
Hi. So
Hey,
question.
Nice to hear your voice.
Yes, nice to meet you, Mark. So a question, if you consider third order, but I mean, all you consider are quasi-linear, so they are linear in highest derivative.
Yes.
But since you use, well, of course, like Euler-Lagrange has to be quasi-linear, but you use variational operators. So whenever you apply them, you get quasi-linear, right? So do you need this condition, actually? Do you have examples when your equation is strictly nonlinear?
Yes. Interesting question for a number of reasons. Yes, interesting question. And I want to put this on there because it's also another component that showed up in this. Can you see my screen?
Yeah.
Okay. This is kind of curious, and I didn't really go too far into it. It was just more of like, oh, okay, that's interesting. Let me see. Oh, yeah, here we go. Okay, this equation right here. Okay.
Yeah.
Can you see it, Boris?
Yes.
Yeah, kind of nasty. And so what happens in this case, and I didn't want to go into this too much, but here's this conservation law right here. Okay. Can you see what I'm underlining? This 1-1 conservation law. Okay.
Mm-hmm.
And this 1-1 conservation law, if I take its vertical derivative, it does give you a 1-2 conservation law. So one could say, well, wait a minute, what's going on with 1-1 conservation laws? And what happens with this is there is a variational operator, okay? And I could put it on the screen if you wanted, but there's a variational operator that annihilates the right-hand side.
Okay.
Yeah, kind of bizarre, right?
It's kind of trivial, yeah.
Yeah, so that's actually what that cohomology, that 1-1 cohomology measures. In fact, it's kind of interesting. I can't remember if I wrote this in the paper or not, because you always wonder, what are these things measuring? These are measuring the variational operators which annihilate the right-hand side. So I don't know what those are called. They're, you know, yeah, I don't know. It's like there's a trivial symplectic form for this equation. I don't know. Maybe, yeah, there's like an evolutionary vector field that's kind of in the kernel of the symplectic form. Yeah, I guess that's what's happening. Yeah. That's what it's finding here. So this is pretty nonlinear, and there is a variational operator, but it's kind of bizarre because it annihilates the right side.
Mhm.
So the symplectic form here is degenerate on this evolution equation. Yeah, what are those called? Oh, I see a chat. Oh, the RAF, he's got to go. Okay, hey. Great.
Mhm.
Yeah. So does that sort of answer the question? I didn't really go too. I did a few examples where I assumed like the equation was quasi-linear or linear in the third derivative, but I didn't really get too far with that, eh? But definitely some interesting things with this nonlinear equation, having this weird cohomology class, eh? So there is a variational operator, but it gives rise to a trivial Lagrangian.
Mhm.
At least for the, you know, for the right-hand side term.
Okay. More questions?
Anyway,
Okay,
it was
Mark. Yeah. Yes.
is there any more questions?
It seems that they are exhausted. Mark, thanks a lot.
Yeah,
I
yeah.
hope-
Hey, Boris, nice to hear from you. Say hi to Dennis and everybody.
Oh, this is not the last talk of you.
Oh, I don't know, eh?
Oh,
But it
we'll
was-
see. Okay,
Yeah, it
but
was, you know, yeah, go ahead.
yes, you are always welcome.
Well, thank you. Maybe
Yeah.
when I get some more progress on the stuff I'm doing with Ivy,
Yeah.
I can
Just let
talk,
me
eh?
know.
Yeah.
Okay.
So is that it?
Thanks a lot.
All right. Well, hey, thanks, Joseph, and I hope you guys are all doing well out there, wherever anybody is. I see there's people from all over the place. And if you have any
Oh.
questions, send me a message about it.
Yeah, sure.
This was
sure.
it was a pretty dense paper, eh? I've been thinking about it a long time, and you know, not very easy to read, I would say. But thank you for letting me try to explain what was in there.
Mhm.
Okay.
Okay. Thank you very
Goodbye,
much.
everybody.
Yeah. Everybody have a good evening.
Well, bye-bye and see you next
Yeah.
Wednesday.
Nice to see you there, Joseph.
Goodbye.
See
Bye.
ya.